Hey everyone, welcome to The Explainer. I am super excited you're here today. If you're the kind of person who just loves to strip away the noise and get right down to the core mechanics of how our universe actually operates, well, you're in for a treat. Today we're unpacking a really fascinating source text, the principles of momentum, impulse, and collision dynamics. More specifically, we are looking at a foundational set of physics standards, PS.Phy.3 to be exact, that basically dictate how we analyze motion and collisions. We're going to break down these somewhat dense principles together into really clear visual concepts. It's totally going to change how you look at objects moving around you.
Okay, let's dive right into this. Here is our roadmap for today. First up, mastering momentum and impulse. Second, the conservation principle. Third, elastic versus inelastic collisions. And finally, unpacking Newton's third law. Let's get to it.
Section 1. Mastering Momentum and Impulse, the foundational players on our one-dimensional track. So, to really wrap our heads around this without getting overwhelmed, I want you to imagine everything happening on a totally straight, single-lane track.
Now, on the straight track, we've got two main forces driving the action, momentum and impulse. Think of momentum as the actual oomph an object has while it's moving. It's the pure state of its motion. And impulse, well, impulse is the catalyst. It's the thing that comes in and actually changes that momentum. They're kind of a dynamic duo. Momentum is the ongoing state, and impulse is the mechanism of change.
It's all well and good to picture one single object just gliding smoothly down a straight line. But physics gets way more interesting when things actually interact. So the big question we have to ask ourselves, and really the question our source material forces us to look at, is this: what happens when these moving objects actually meet?
That brings us nicely to Section 2, the conservation principle, analyzing motion before and after.
So the crucial point is right here in the standard, which says, analyze the motion of objects based on the principles of conservation of momentum and impulse in one dimension. I literally cannot overstate how important that one-dimension constraint is. By restricting everything to a single straight line, we don't have to worry about an object glancing off at some weird 42-degree angle. Everything is either head-on or trailing behind. It keeps our focus brilliantly sharp, so we can purely observe the conservation, that unbroken chain of momentum transferring from the before to the after.
Which brings us to the main event, Section 3, Elastic versus Inelastic Collisions. It's time to start modeling 1D crashes.
And this brilliantly illustrates the conceptual divide we're dealing with. In an elastic collision, objects smash into each other and dramatically bounce apart. But in an inelastic collision, they crash, stick together, and keep moving forward as one big mass, kind of like two freight train cars coupling together on the tracks. But here's the universal rule linking them both: conserving momentum. Whether they bounce or stick, the total momentum of the system on our track stays absolutely constant. The standard is demanding we understand that conservation happens no matter what the crash actually looks like.
Just to cement this, let's look at the exact breakdown. First, we confine our variables to a single dimension. Second, we apply the conservation of momentum as our ultimate rule. And from there, we actively use models to analyze both inelastic sticking scenarios and elastic bouncing ones. We're not just memorizing stuff here. We are building models to predict exactly what the after picture will look like, based entirely on the before. Okay, let's take a quick cognitive breather here. We've got our straight track, our moving objects, our bouncing and sticking rules, and we know momentum is completely conserved. But why? What is the underlying mechanical rule that forces momentum to balance out so perfectly every single time? Where does Newton's third law fit into all this? And that brings us to the final act of the explainer, Section 4, Unpacking Newton's third law, the underlying rules in mathematics. Let's move to and see how this builds when we bring in computational thinking. The source gives us a really clear sequential process to analyze this. Step 1, utilize mathematics, to actually quantify the mass and velocity. Step 2, apply computational thinking by breaking the crash down into logical, bite-sized steps. And Step 3, analyze relational variables. That basically means seeing how changing just one little piece, like the speed of one train, directly ripples out and affects the whole system.
Now, what's really interesting about this slide is how cleanly computational thinking maps these relationships out. Take impulse, for example. Its relational impact is that it triggers change. And why? Because of Newton's third law. An equal and opposite force is being applied over time during that crash. Then look at momentum. Its impact is the conserved outcome. Again, Newton's third law steps in and guarantees an equal and opposite momentum transfer between the objects. The math, the models, the physics, they literally all align perfectly on our 1D track.
So, let's tie the whole shebang together.
We start off by confining our view to 1D conservation principles. We use models to visually map out elastic and inelastic collisions. We apply mathematics to get the hard numbers, and finally, we connect it all right back to Newton's third law using computational thinking. It's just a beautifully cohesive framework where every single concept builds on the last one.
Which brings us to a final, kind of mind-bending thought to wrap up this explainer. The standards we just went through are rigid, right? They lock us into one dimension with very specific math and models. But the physics they describe governs our entire reality. So I want to leave you with this. If every interaction in our simple 1D model strictly conserves momentum, how many hidden collisions are transferring momentum right around you at this exact moment? From the air molecules bouncing off your face right now, to the sound waves hitting your ears, the conservation of momentum literally never stops. Thanks so much for joining me today, and keep looking for the physics happening right in front of you.